Hello and welcome back. Here's the second part of section 3.6, and this is where we're going to learn to solve absolute value functions. So let's go back and remember our definition of an absolute value function. G of w equals absolute value of w, which is equal to minus w if w is negative, and w itself if w is greater than or equal to 0. So let's start with a really straightforward example. Let's say we want to know where, for what values of w, g of w equals 10. So in essence, we're solving absolute value of w equals 10. Well, there's two cases here, right? We know that one case is that w is positive 10, and if we take the absolute value, then we get 10. The other case is w equals negative 10. We take the absolute value of negative 10, we still get 10. So when you're solving absolute value equations, you have to do a positive case and a negative case for any part that's under the absolute value. Let's look at an example. So this example, here's a little blurb about isolating the absolute value first. That is absolutely true. The first example doesn't have anything multiplied outside the absolute value, so we can just go ahead and solve this. We want to know where f of x equal to absolute 2x minus 3. We want to solve for all values of x to make that equal to 8. So we want to solve absolute value 2x minus 3 equals 8. So we have two cases. Either 2x minus 3 computes to positive 8, or it will compute to negative 8, and then we take the absolute value and we get positive 8. So you have two linear equalities to solve here. Add 3, 2x equals 11, x divided by 2, x equals 5.5. Or add 3 to each side. 2x equals negative 5, x equals negative 2.5 divided by 2. That's 2.5 negative 25. So I got two solutions, x equal to 5.5 and x equal to 2.5. Let's check those because checking is always a good idea. So let's go ahead and check our answers over here to the right. Check. Let's plug in x equal to 5.5. So that would be absolute value of 2 times 5.5 minus 3 and your absolute value. 2 times 5.5 is 11 minus 3 is absolute value of 8, which is 8. Let's go ahead and check the other one too, just for the fun of it. Check x equal to negative 2.5. So 2, plugging in negative 2.5 minus 3, absolute value. 2 times negative 2.5 is negative 5 minus 3 is negative 8 in absolute value, which is 8. So we checked both our answers there just by plugging in it. That's one way you can check it. All right, let's try a little bit harder absolute value problem, the second one down here. And this one has stuff going on that's not inside the absolute value. So the rule there is you need to make sure, okay, I'll remember there's a Java update available. The rule there is that you need to first get one side completely equal to absolute value, and then you can break it into cases. All right, so we want to solve s of t equal to 4 minus 2 times the absolute value of t minus 1, and we want to solve for s of t equal to 1. So we want to solve 4 minus 2 absolute t minus 1 equals 1. So the first thing we're going to do is we're going to isolate the absolute value. And so I'm going to get the negative 4, subtract 4 from each side to get rid of that 4 plus on the end. Minus 2 times the absolute value of t minus 1 equals 1 minus 4, which is negative 3. Now I want to get rid of this, multiply by negative 2, so I'm going to divide by negative 2. And that gets me the absolute value of t minus 1 equals negative 3 divided by negative 2, which is 3/2 or 1.5. Let's just write 1.5. You can always write things as a decimal as long as you're not rounding. All right, now we're at the point where we can break it into two cases. Either t minus 1 will compute to positive 1.5, or t minus 1 will compute to negative 1.5. Add 1, that means t is 2.5. Add 1, or t is negative 1/2. So those are my two solutions. I'm not going to check it right now, but it'd be good practice for you to go check it right now. All right, now that we can solve absolute value equalities, let's try and solve for horizontal intercepts of a function. in general, not even for absolute value functions, for all functions, how do we find the horizontal intercepts? Remember, for any function, just draw one, the horizontal intercepts are where it crosses the x-axis. So here's my horizontal intercept, here's a horizontal intercept, here's a horizontal intercept. This guy right here is also a vertical intercept. So how do we solve for horizontal intercepts? Well, you set the output of the function, set f of x equal to 0, and you solve for x. You want your output to be 0, or your y value, your height, to be equal to 0. So with absolute value functions, there's going to be either 0 horizontal intercepts, that should say horizontal. There could be 0 horizontal intercepts, 1 or 2. Let's just draw pictures of what that looks like. So an absolute value function could look like that, and it has no horizontal intercepts. It could be completely above, or it could be completely below the x-axis. If it had 1, maybe it just comes down like this, like right, and just touches and comes right back up. That would be 1 horizontal intercept. Or we could have one that comes back, crosses over, and backs up, and then we would have 2 horizontal intercepts. So those are the 3 choices. You can't have more than that. So let's try a practice problem. Let's find the horizontal intercepts for k of x equal to 5, absolute value of x minus 2 minus 3. So we're going to set it equal to 0. And now we're just right back in solving absolute value equations. So we need to isolate the absolute value. So I'm going to add 3 to each side using my reverse order of operations. 5, absolute value of x minus 2 equals 3. Divide both sides by 5. Absolute value of x minus 2, let's cancel, equals, and I'm just going to leave that as 3/5. You could make it 0.6 if you wanted to. And so now I have 2 cases. My absolute value is isolated, either x minus 2 equals 3/5 or x minus 2 equals negative 3/5. So solving this one, we add 2 to each side. 2 plus 3/5 equals 2 3/5. And add 2 to this side. X equals, well, 2 minus 3/5. Remember, 2 is the same as 10/5. 10/5 minus 3/5 is 7/5. Or you could write 1 2/5. All right, so that's how you find your horizontal intercepts. All right, let's try solving absolute value inequalities. Now, so far I haven't graphed any of these functions using Desmos, but here's an example of where I think using Desmos is really helpful. So the graph we're going to try and graph on Desmos is this graph right here. We're going to solve for the function h of t equal 3, absolute value of t minus 1 plus 1. We want to find where that function is greater than 7. Okay? We want to find where that function is greater than 7. So let's go look at its graph. All right, here we are in Desmos, and we're going to go ahead and graph this function. H of t, I think that's what I called it, equals 3, absolute value, t minus 1. Now in my parentheses, because that's the end of where I want my absolute value to be, plus 1. Now hopefully we are familiar enough with our graph transformations to know this is the regular absolute value function, shifted right 1, shifted up 1, and stretched vertically by 3. But anyway, Desmos does that all for us. All right, here is our function h of t. We want to know where this is going to be greater than or equal to 7. So for fun, let's just go ahead and graph y equal to 7. Oops, that says y minus 7. Let's do y equal to 7. And zoom in a little bit. So here the function values are 7. This is a point -1, 7. So if I put -1 in, I get 7 out. Here my function values are all less than 7. Here, for example, it's function value of 4. Here's a function value of 0, up and so forth. And here is where I hit 7 again. So anywhere between -1 and 3, it's not going to be equal. It's not going to be equal to 7. Anywhere between -1 and 3, it's going to be less than 7. And anywhere from here up until -1, and then from 3 on out, it's going to be greater than 7. So we have this picture in our head now of what this absolute value function looks like. Let's use that picture in our head that we have to go solve the problem algebraically. All right, so let's try to solve this algebraically. So what do we want to do? Well, we'd like to find out where the function equals 7, and then those are going to be the cross points, and then we'll know where to put our endpoints for our intervals. So we're going to solve where it equals 7. And you may say to me, Nicole, I already know where it equals 7 because I saw on the graph it was like -1 and whatever that one was, 3 or whatever it was. Yes, we do, and it got lucky on this graph that it equaled 7 at exactly a nice integer value that you could read off your graph. But this is how we would do it if it was an irrational value or a really ugly fraction or something like that. So let's solve it equal to 7. Subtract 1. 3 times absolute value of t minus 1 equals 6. Divide by 3. We get absolute value of t minus 1 equals 2. Break this into my two cases. T minus 1 is 2, or t minus 1 is -2. Plus 1, t is 3. That's one of them that we had. T is -1, and that was the other one we had. Let's just re-sketch the graph here. Remember, it looked like this, more or less, right? And here was 7, maybe. And we know this happened at -1. Okay, my graph is not perfect. And this happened at 3. So we know from 3 on out, and from it's greater than 7, and from -infinity up to 1, it's greater than 7. So let's trace that on our x-axis, and then we can write our answer in interval notation. So from -infinity up to -1, circle at -1, circle at 3 because it's strictly greater than, up to infinity. So our answer is -infinity to -1 union 3 to infinity. All right, let's try one more of these guys. All right, one less example for you. I'm actually going to change the example right now because I wrote down one that I don't really want to do. I want to do, for what values of t is f of t less than or equal to 0? That's what I want. So we're just going to cross that out. Given f of t equals absolute value of t minus 3 minus 5. Now this is a very straightforward function transformation. So I think we can do this one by hand. We know it's going to be right 3 and down 5 from our original absolute value equation. So let's draw a graph of this guy. Good practice graphing by hand. All right, so let's get our scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. Let's label some of these. 1, 2, we know we need to go down at least 5. 3, 4, 5. All right, so what was at 0, 0, our vertex of our absolute value function, is now right 3 and down 5. So down here, we remember that the absolute value function is made of minus x, the graph of minus x and the graph of x both have a slope of 1. So if I go down, rise over 1, if I go up 5, I need to go right 1, 2, 3, 4, 5. So that's the right-hand side. And if I go down 5, I need to go 1, 2, 3, 4, 5, back 5 to get the left-hand side. Let's see, make sure I did this right. 1, 2, 1, 2, yeah, 0, right there. Okay, here we go. Just like that. And there's a graph of f of t. Now, if you need Desmos to help you, that's fine, but this is a good way to practice your graph transformations. Now, we want to know where what values of t is f of t less than or equal to 0. Well, we can see on the graph anywhere between -2, that's where it equals 0, and 8, it's going to be less than or equal to 0. But let's solve this algebraically in case we come up with one that doesn't have quite such nice endpoints. So we're going to solve the equality first. We're going to find where t minus 3 in absolute value minus 5 equals 0. Find our edge points of our interval, and then we know to pick in between because we looked at the graph. So add 5 to each side to isolate the absolute value. T minus 3 equals 5. Break into my cases. T minus 3 is going to either produce a 5 or it's going to produce a minus 5. Add 3 to each side, so t is equal to 8. That's one of my endpoints. Over 8 up 0, right? That's this one. Or add 3 to each side, and t equals -2. That's my other endpoint, -2, 0. And we know the answer is from -2 to 8 inclusive, because we looked at the graph and we saw that that is where the function is going to have values less than or equal to 0. All right, so this ends our section, and go ahead and start the homework.